Thank you very much, and I'd like to thank the organizers for inviting me over for this very interesting and kind of small workshop with a lot of interesting discussions. Okay, so I'm going to tell you about two Josephson junctions, and that's the sort of common thread in between. The first one is actually an amplifier, a quantum noise limited amplifier using graphene Josephson junctions. And the second is using high temperature superconductors, trying to make a non-reciprocal device in the superconducting regime. Okay, so the gory details of our work are in these two papers. I'll try to get to most of the essential details, but if you have questions, please feel free to ask me, or you can look at these references. So I gratefully acknowledge the funding from different agencies in India which make our research possible. So let me get started. I want to front load the acknowledgements. So these are the people who do the difficult and challenging work. My student Joydeep led this work on parametric amplifier, and my collaborator is R. Vijay, an expert in qubits and stuff, and superconducting analog. Okay. And the work on the Josephson diode was led by my student Sanat, and we have very good high quality crystals from my colleague Tamil Vale. We make our BISCO crystals ourselves. And for theory, we collaborated with Felix von Appen at Berlin. So let me get started with the talk. Of course, we benefit from the very nice HPN from NIMS. So let me give you a quick outline. So I'm going to thread this talk by using Josephson junctions of two different varieties. So I'll tell you why they're interesting. Many of you already know of them. But let me, for pedagogical reasons, let me just cover that aspect quickly. Then I'll tell you about how one realizes these Josephson junctions. Then I'll jump into sort of the main part of my talk, which is using graphene Josephson junctions to realize a quantum noise limited amplifier. Then the second kind of Josephson junction, which is by twisting two layers of BISCO, you can realize a very nice Josephson junction with non-reciprocal response. And it has potential for interesting technologies, and more work needs to be done to demonstrate it as a technology. Then I'll try to quickly give you a flavor of what's exciting or interesting going forward with these kind of devices. So what are Josephson junctions? We all know the property of superconductors that makes them very unique is this macroscopic quantum property, which is a macroscopic wave function that defines a superconductor where the Cooper pairs are paired electrons. And irrespective of the kind of superconductor, this physics is central to all kinds of superconductors, either S wave or D wave. Now, Josephson junctions as envisaged in sort of the canonical sort of geometry for which Josephson proposed these devices first, and then experimentally they will realize later, is this superconductor interrupted by a thin insulator and then another superconductor. And what really happens is that the sort of this quantum state of the superconductor is defined by this complex sort of wave function, if you like. And when you have sort of the wave amplitude of the wave function, it sort of decays through the insulating barrier, and then there's an overlap with the other superconductor. And what that really leads to is a Cooper pair formed in one part of the superconductor can transfer to the other part of the superconductor interrupted by the insulator, and this transfer of these Cooper pairs is the Josephson effect, and you get a dissipation-less transport of current through the system. There are variants of these Josephson junctions, and you can realize Josephson junctions with slightly different physics, but at the heart of it, you can interrupt the superconductor by a normal material. In our case, it will be graphene. And here, the transfer is not of Cooper pairs, is not by sort of tunneling-like physics, but because of formation of Andreev-bound states, reflection of electron on one superconducting interface results in a hole, and then when you have a kind of reflection of the interface, second interface, you can have a bound state, and that leads to a net same result, a transfer of Cooper pairs from one side to another. So these are two sort of different realization of Josephson junctions. Now, what it leads to is a very interesting device, as I explained to you, whether they arise from SIS or SNS. They result in a very unique relationship between the current and the superconducting phase difference across the two superconductors. And it also tells you that the dissipation occurs when there is a rate of change of flux through the system, which is sort of given here. So the DC Josephson effect gives rise to a device which has a regime of transport where it's dissipation less, and then it switches to a dissipative regime, and that's sort of the DC response. The AC response is sort of central to many of the implementations of Josephson junctions for quantum devices. And it basically, rate of change of the phase across the two superconductors is set by the voltage that you develops or one applies across it. But what is important for this particular sort of talk is that this device acts, a Josephson junction acts like an inductor, a peculiar kind of inductor, unlike the inductors that we know, because you can do simple algebra to rearrange these Josephson equations into a form which is the definition of inductance. And what you find is that the inductance is actually a function of the current. And it's basically a nonlinear inductor, and that makes it a very attractive device. The nonlinearity is not undesirable, but it's actually central to why they're used in qubits and in these amplifiers that I'll talk about. So it's a inductor, and in my talk I will show you that what we realize is a kind of a nonlinear inductor which is tunable with gate voltage. So it's like a field effect transistor where the resistor is tuned by a gate. Here you have an inductor, nonlinear inductor, whose inductance is actually tuned by the gate voltage. All right, so why are Josephson junctions interesting? Of course, this is well known to many people in this audience. So their superconducting qubits are based on various sort of regimes of an inductor shunted by a capacitor. So you have transmon in one limit. So Josephson junctions are also at the heart of the SI system of units, which is kind of the new definition of the voltage standard. And you have quantum sensors, which, because the Josephson junction are extremely sensitive to perturbation of these, for example, the Mandar bound states, they can be used as very good sensors for variety. So now a lot of work has been done over many decades on Josephson junctions using aluminum, aluminum oxide, and other materials sort of systems. But what is interesting to us and to a large number of people is use the extensive van der Waals library to combine materials with unusual functionalities sitting right next to each other. That's not possible with aluminum, aluminum oxide based technology, and that's sort of the focus of our efforts in this area. So the first example of unusual kind of use of van der Waals system is this sort of making a low noise, in fact, a quantum noise limited amplifier. And you might say, why does one need a low noise amplifier? So whenever we have some sort of a quantum system, either it can be a qubit or some sensor, you want to amplify the electrical signals over many orders of magnitude. Okay, and that because at room temperature, whenever you are processing that information and digitizing it, the power has to get amplified. And there's a change in temperature as well. So you need an amplifier for sure, but an amplifier does two things always. It amplifies the signal, but it also adds a noise, which is an intrinsic property of the amplifier. So, and thermodynamics basically says that you cannot have noiseless amplification. You can minimize the noise added depending on the principle of operation of the amplifier, but you cannot get rid of the noise. Okay? So this noise added needs to be kind of controlled for many of the quantum applications. Now, a single amplifier is not used in amplifying these signals. Often you use a chain of amplification sitting at various temperatures and based on fundamentally different principles. So you have, let's say 2 amplifiers. So then, this second amplifier and first amplifier provide different gains, but the added noise of each of the amplifier is benchmarked in terms of a noise temperature. So the larger the noise added by the amplifier, the larger is the temperature. So the gain of this chain is a product of the gains, which is sort of intuitive. But the noise of this chain of amplifiers, it has a peculiar expression, which you can actually make simple arguments and derive. The total noise of the system is the sum of the noise of the first amplifier plus this sort of peculiar looking expression. So this contribution of noise of the other amplifiers can be reduced if the gain of the higher sort of down the line amplifiers is large. But you cannot reduce the overall noise of the system less than the first noise of the first amplifier. So you want the first amplifier to be the one which adds the least amount of noise allowed by quantum mechanics. And that's the need of this low noise, quantum limited noise, low noise amplifier. So that's what we implement using a graphene Josephson junction. So I should say that this is an old idea, parametric amplification, quantum noise limited amplification, and has been extensively used based on superconducting aluminum oxide based Josephson junctions, and it's a workhorse for all kind of qubit measurements. So it's an unusual kind of amplifier, so let me just give you the basic of it. I won't go too much into it. So this is a kind of equation that we all sort of know and love, which is a damped harmonic oscillator. And we can write down what happens to the amplitude as a function of time. In a particular regime, if you imagine you have a spring constant, which is this omega naught, can be modulated in time, you can realize something interesting. This term B is a stand-in for damping in the system. And when you have a spring constant, so imagine you have a mass attached to a spring, and the spring constant itself is changing in time. This is sort of that implementation, which is called parametrically driven harmonic oscillator. And the solution is interesting because in the denominator, the damping is counteracted by this drive, which is the parametric drive, which is the modulation of the spring constant. And so you basically counteract the damping. Sort of, you can see that it can actually be harnessed to kind of realize kind of amplification. And that's at the heart of this kind of amplifiers. Why they are quantum noise limited will come in a minute. So if you have been in a swing at some point of time and nobody's actually externally pushing you, you basically already implemented this amplification of the mechanical motion by this parametric process. You basically change the effective length of the pendulum. Okay, so this idea is used in optics and lots of different physics and technological fields. So in Josephson junctions, you can also realize the same physics, which is central. So you have a Josephson junction shunted by a capacitor and kind of some resistor. This is the equation of motion for the phase of the system. And if you keep leading order terms, so this is the current phase relationship, which is kind of important to all kinds of Josephson junctions. So if you keep the leading order terms, you have this nonlinear term, which is a cubic nonlinearity, just expansion of phi, sine phi. This plays a very important role in making all kinds of qubits and certainly this amplifiers. So this nonlinearity is a good thing, as I'll show you in a minute. So effectively, mapping back to the equation of motion of a mass attached to a spring or in a pendulum, you get the same sort of thing, but now there's a cubic term. And in the right sort of parameter space, this equation can be rewritten as exactly the parametrically driven harmonic oscillator. Okay, so this, you'll have to take it from me that you can do this algebra to result. So this is the starting point that I told you is the way to get amplification. And so the way it works is that the system, now your Josephson junction shunted by a capacitor, like a resonator, acts like a nonlinear medium. So you can send in a second signal and your signal that pump rather, and you can send your signal, and there is basically a nonlinear process which ends up amplifying the signal, which is of interest to you. Okay. So most of the times people have been using Josephson junctions using aluminum oxide based technology, make a squid, thread flux through it, and you have a Josephson junction which is tunable with flux, which is nice, but there is kind of certainly an interest in making this kind of amplifiers, which is not tunable by magnetic field because it can do bad things in your superconducting measurements apparatus. So you would like to have something which is tunable with electrostatically with a gate, and you can tune it fast. And that sort of forms the primary motivation for our work. Now, why is it quantum noise limited? This is a one-slide summary of why this works. So you have a nonlinear sort of oscillator. So in the small amplitude, it behaves like a nice Lorentzian amplitude as a function of frequency. But when you drive it nonlinear, you see its response is no longer Lorentzian, but it sort of bends to the one side depending on the sign of the nonlinearity. And this is the part where it's the sharpest, which is a peculiar point called the bifurcation point. If you send in now the signal, it bounces off this very sharp curve, and its signal comes out amplified. Now, the reason why it's quantum noise limited is that these oscillators are essentially harmonic oscillators. They might be unharmonic, but they have energy level structure. And if you make this device and set it at low temperatures compared to the separation between these harmonic oscillator states, you basically have nothing else to add noise but the 0-point fluctuation of this kind of inductor and a capacitor in parallel. And that's really where the noise added comes in. It's the noise added by the quantum fluctuations of this quantum circuit sitting in the ground state, h cross omega by 2, and divided by the Boltzmann constant.
But if you have photons, you are not in the ground state.
But you drive it, you mean when you drive it nonlinear, you still drive it, eventually you drive it very, very hard, that you will start going away not in the ground state, but at low powers, you're still in the ground state. So we are interested in making these kind of devices, but because you want kind of new architectures for making these kind of amplifiers in high magnetic fields. And you can actually make some exquisite bolometers using this fundamental building block of a parametric oscillator. And so the way we make it is using graphene Josephson junctions. And there has been a lot of work over the last some 9 or 10 years trying to make graphene Josephson junctions and making different kind of superconducting circuit elements, including qubits, which was a very nice talk yesterday. Was mentioned in the talk yesterday, and this is a transmon qubit, and there are lots of sensors. So there is a lot of interest in graphene, and particularly for sensing, graphene is interesting because it has very low electronic specific heat. So you want to make bolometers, this is a great way to do it. So this is sort of a diagram of our device. So we have a Josephson junction, I'll show you an image, and shunted by a capacitor, and this is sort of a way to launch and reflect the RF signal of the device. And this is an optical microscope image, and so buried between the stack of graphene Josephson junctions and inside boron nitride, you have the Josephson junction, and you have a capacitor, and now you're ready to kind of play with the device. The effective circuit is you have the Josephson junction, which has an inductor and a capacitor shunting, and there is some loss, which is the subgap resistance, which determines the overall quality factor of this resonator. And so when we measure the DC electrical property of the device, it looks, as a function of gate, it looks like a very nice Josephson junction with a dissipation-less branch here, and then you switch it out of the superconducting state into a dissipative state. This is on the electron side. On the hole side, you don't see symmetric effect because of Schottky barriers, which are formed because of the metal contacting the graphene. This is kind of universally seen to a varying degree by groups all over. It's always on the hole side, you will get a poorer Josephson junction because the transparency is bad. So now the same device, because it's already hooked up across a capacitor, you can make, it's a resonator, so you can, instead of measuring DC electrical property, you can measure the resonance of that circuit as a function of gate voltage. So today I'll just focus on the electron side. So what you see is a phase of it's got phase change across the device, and you see that this white contour is the variation of the resonant frequency of this oscillator as a function of gate voltage. So you have a resonator, LC resonator, whose L is being tuned by a gate, and so you basically get a tunable resonator, which is at the starting point of the amplifier. So it can be tuned from something like 2 gigahertz all the way up to 5 gigahertz. So it's a large tunability. So depending on what kind of electrical signal I want to amplify, I can tune the gate voltage to that right regime. So let me just talk about a particular value of gate voltage just to demonstrate how the amplifier works. So now we have a linear oscillator, and we can drive it nonlinear by kind of going into the nonlinear regime, and you can see this phase sort of bend to the left. That's the resonance, and at this point it works like an amplifier. So you see a gain of the signal that is reflected back from the device. So this is the gain, and it's a gain of about 23 dB. And what's more important is this red scatter plot, which is the added noise by this device, and the green line is the quantum limit, which is h cross omega by 2 kb. Okay, so it's a quantum noise limited amplifier, and you can do a lot of fun things with it. So this amplifier is comparable sort of to the best discrete parametric amplifier made by other technology, which is aluminum oxide based technology. So I won't have time to go fully into the second talk, but let me give you a glimpse of it since I kind of promised. So the second talk looks at a particular superconducting device, which is a non-reciprocal device. So we know one kind of non-reciprocal device in the normal regime, which is a PN diode, which everybody has used, and it's ubiquitous. It's there everywhere in all the electronic devices. So it relies on breaking this fundamental symmetry, which is the inversion symmetry has been broken in, structurally inversion symmetry has been broken in the PN junction diode. Because the p-doped side is not equivalent to the n-doped side, so the inversion symmetry is broken. So there has been a lot of interest in the last several years on realizing a superconducting version of it where you break inversion symmetry and time reversal symmetry. And what you realize is a device which is in the superconducting regime. On one side of the one bias of the current, it has a larger switching current than the other. That is the superconducting diode, and a particular version of it is the Josephson diode, which is, I'll try to give you a glimpse. So there's been a flurry of work over the last couple of years in lots of different kind of devices. But these are all devices working at 4 Kelvin or less, and the asymmetry, which is this difference in the current on plus side and minus side, can be often very, very small. What we demonstrated is a device with BISCO, which works as a superconducting diode all the way up to 77 Kelvin and has very large asymmetries of something like 60% at 30 Kelvin. Okay, so how much time is it over? Okay, let me proceed. It will be a little bit rushed, but my student Amit is going to present a poster sort of extending this work, so this might serve as a good advertisement for that poster. So BISCO has been studied for decades, high temperature superconductors. Many aspects of the microscopic mechanism are not understood, but what everybody agrees on is that it has D-wave symmetry, and it has some superconducting gap and a very small coherence length. And it's a layered structure like shown here, and the superconductivity arises from these copper-oxygen planes, and the other strontium oxide and bismuth oxide are kind of buffered layers. And across this direction in the c-axis is basically Josephson coupling of these copper oxide planes with each other. So it's inherently a 2D superconductor coupled by Josephson physics in the third direction. Okay, this has been demonstrated very nicely as well. So these are aspects that everybody agrees on, and which is what I'll use. Exact microscopic mechanism and the parent state and how it arises is not fully sorted out. Okay, so a lot of people in this field got excited because there was this theoretical proposal by Marcel Franz's group that you have twisted layers of BISCO, you can realize a kind of topological superconductor by rotating 2 layers of BISCO by 45 degrees relative to each other. Because of the D-wave order parameter, when you twist it in this direction, and you will basically can get a tunneling of co-tunneling of Cooper pairs rather than tunneling of Cooper pairs, because the two lobes basically fall in between the minima of the other. So this proposal is sort of very exciting and motivated a lot of people. And so we started making these devices. These are a little bit challenging to make. Unlike graphene, you cannot do the cutting laterally, which is sort of commonly done in graphene. Is to take graphene and then you slice it to create two daughter pieces of visco or graphene. Here we actually peel off one layer from another at a kind of a stage which is cryogenic, because we don't want the oxygen to get degraded with time. Okay, this copper oxygen bond is good, but the oxygen is metastable in these materials, and if you just sit it on a lab table, it will degrade within a matter of few hours. So we peel off these crystals when the crystal is still at something below -100 C. And then we peel it off and then we put it back after rotating by the right angle, and you get a Josephson junction in this overlap region. So we put electrodes by shadow mask. You can't do lithography on these materials because they degrade with time. If you know shadow mask, you align and kind of stencil and you evaporate metal through it. And you have lots of electrodes to measure different properties of the original superconductor and also the Josephson junction formed. So our device, which gives this non-reciprocal response, is this interface where inversion symmetry is broken because of twisting, the first layer, and that's sort of the heart of the device. Because of the time, I'll show sort of the main results, that if you measure this device, the switching current, because it's a Josephson junction, is different on two sides. So inversion symmetry is broken, and very small magnetic field can break the time reversal symmetry, and you get a diode, which is a Josephson diode. And that's sort of the main. There are similar results from Philip Krim's group where they see kind of similar diode-like physics. This is a diode which is tunable, Josephson diode, which is tunable with perpendicular magnetic field. So this is a cartoon of the stacked device. This purple layer is the operative important part of the device, which is the Josephson junction, and which is this twisted Josephson junction. And you can measure this asymmetry as a function of small magnetic field. It's tunable with very small magnetic fields, of the order of Earth's magnetic field. So we had to do special arrangements to null out external Earth's magnetic field, and inside that apply small magnetic fields. So you can tune the asymmetry from 60% to -60% in these kind of devices with very small magnetic field corresponding to 1 quanta flux through the Josephson junction. Okay, so I will stop here because of the time, but this junction behaves like a very nice Josephson junction, but with this non-reciprocal response. And the properties can be understood because of the D-wave symmetry. So the maximum asymmetry is seen for 45-degree twist. Right here. And there are lots of fun things that can be done. I'll stop with what next, and thank you very much for your kind attention.